conclude this discussion about renormalization and regularity structures for dynamical morphic.
Okay. Okay, yes. So I have prepared a couple of really very simple examples in order to separate difficulties. Okay, so here they all look mixed together, and yeah. For instance, let's discuss 540. Okay, so this may be insulting, but for me it was not so. It was instructive to write this slide. So you want to study on R, okay? So this probability measure for lambda parameter greater or equal than 0. So it's the Gaussian measure perturbed by this quartic potential. Okay, you may recognize something. So you consider the partition function. Okay, you notice that this again for lambda positive is C infinity, and you can compute derivatives. So I hope this is correct. At 0, so you get this coefficient, okay?
At 0, it's not C infinity. At lambda equals 0, it's
well
0 plus.
0 plus. So on R plus, I didn't define this for negative lambda, okay? So if you want, it's differentiable on positive lambda, but then you have limits at 0. Okay, so you see it's not so trivial. And then you can expand z lambda around 0. Okay, again for positive lambda, so non-negative lambda, and you have this expansion. Okay. The series is not convergent because an grows as a so like something like 2n, the factorial of 2n. So this is not convergent, but you can stop at finite n, and you have an error, a remainder that you will try to estimate in some other way. Okay. So as far as I understand, this is a toy model. Again, maybe it sounds insulting to some of you, but what I understand from this is that I have a series which is not convergent, but the terms that appear are one by one accessible. So I know what they are. Okay, so is this correct? So is this more or less what may happen also in other slightly more complicated situations?
It's a divergent asymptotic extension.
Exactly. Wow. Okay. So I have understood something at least. That's good. Now I want to apply the stochastic point of view. So the Parisi-Vu approach. Okay. So again, they will be outraged that I call this in this way, but so I introduce a SDE which has as a drift, so the gradient of the potential which appears inside this exponential divided by 2. So this is this dt plus dB, where B is a standard Brownian motion. Okay, so this SDE has mu lambda as its unique invariant measure. So this more or less can be proved fairly easily. So now I introduce a regularity structure, so it's not really necessary. So you can solve this in a very classical way. There is not even a stochastic integration, so it's really very simple. But okay, so just to show you what you get. So here you need 3 symbols. So one is, so the first is 1, the second is B, which represents a Brownian motion, and the third is X, which represents time. Okay, I could have called T but okay, I kept the notation of x. And then what do? I collect here the coefficients with respect to this basis of monomials. Okay, so you remember ut is my notation. Okay, I have defined the model, but okay, this is for completeness, but it is quite simple. Now at level 1, I have the value of my object, which is xt. At level b, I have the okay, maybe I can write. Okay, maybe let's just write this. No, so it's small x. So you write this in the integral form, okay? So minus 1/2 xs minus lambda 2 xs cube ds plus pt. Okay, then what do? So in fact you consider increments of this x minus t minus x minus s. Okay, by some simple argument, you will write this like that. Cube, so this is times t minus s, okay, plus bt minus bs, plus a remainder of order t minus s. I wrote here 1 plus kappa, okay, 1 plus kappa here. So you see, essentially this formula means this. Okay, I am computing coefficients with respect to my monomials. So the monomial which represents b has coefficient 1, so here I put 1, and the monomial which represents t minus s has this coefficient. Okay, I replace now t by s, but okay, it's the same. Okay, so so you see here I have a finite sum. I have 3 terms which remain 3 forever in this setting, but the complexity is inside the coefficients, which are not explicit anymore. They are solutions of some nonlinear equation. So I can approximate, I can, right? But if you compare that, because so this is a reaction to David's question yesterday about an infinite sum. There is no infinite sum here. Maybe.
Yeah, so I understood finally that the infinite sum is actually inside the coefficient.
Yeah, the infinite operation is what defines by iteration of a map x as a fixed point, blah blah blah. Okay, so this shows a bit in a concrete situation the 2 approaches. It's a first success of the semester. Okay. Okay, and then I had another question about this reconstruction. So I want to show again an example which may be instructive. So well, this is again the same result as yesterday. So okay, let's consider a function. Okay, I called it b because it may be Brownian motion, but in fact it may be any function which is Hölder. Okay, which means this kind of control. Now, the derivative b dot is well defined as a distribution, like that, by integration by parts. Okay, so this is the definition of this distribution. Now, if you take another function, f, if f is C infinity, then f b dot is well defined like this. So in fact, you just multiply f and phi, and then you take the derivative of this product. This is again a function in C infinity with compass support, so everything is well defined. Okay, this is okay, but what if f is in C alpha? Okay, it's not C infinity, it's only C alpha. Can you do something like that? So again, I insisted a lot on this problem, which is crucial to define products in situations where you have distributions. And so this is exactly one such situation. Okay, we use regularity structures. and the reconstruction theorem. So here you need just one symbol, it will be enough. So it will represent the derivative of b. So here I have not specified s, but so s is the, okay, for all t you have the same distribution, which is b dot. Okay, this does not depend on t. Okay, so s would be b dot of s, but this is not a function, it's a distribution. So, and gamma is trivial, so exercise, convince yourself that this is a model. That's okay. It's not difficult. Now, what do you do with this? So you define this function, okay, which is a candidate to be in d gamma for some gamma. Now, again, it's very simple. F of t minus f of tu of fu is just that. Now, the definition is that this will be in d gamma if and only if this difference, so you are at level xi, which had this, well, no, it had homogeneity beta minus 1, and so this should be controlled by t minus u at to the power gamma minus the homogeneity, so gamma plus 1 minus beta. Okay, so you need gamma to be positive, and so gamma is positive if and only if alpha is, so satisfies this, alpha plus beta strictly greater than 1. Okay, so suppose this is the case, so you have beta and alpha such that the sum is strictly greater than 1. So for instance, 1/2 is not good, so you need to go beyond 1 strictly, so you suppose this. Okay, then f of t is is ft times xi, which is a symbol, but now you apply pi t to it, and you obtain ft b dot s. So again, it's a distribution in s. Okay, what I tried to say yesterday is that once, so as long as the two variables t and s are decoupled, there is no problem. You have a function of t that you multiply by a distribution in s. That's perfectly well defined. The problem is if you want to evaluate s and t, if you want to couple the two variables, which would be exactly the product of f and b dot. Okay? Okay, now, of course, this distribution in S cannot be evaluated at S equal to t unless b dot is continuous. So if b dot is continuous, you can do it. You put t here, and you have, perhaps you remember, so this formula pi t of f of t, which is the reconstruction of my function in d gamma. But in general, this is not possible. But okay, the reconstruction theorem says that there exists this object R of f such that blah blah blah, and so we define f b dot as Rf, as the reconstruction of this thing. Now, in fact, this is a classical result in harmonic analysis. Okay, if alpha plus beta is strictly greater than 1, then there exists a continuous bilinear operator m from C alpha times C beta into the distributions, which extends the classical product. Okay, so G dot here is well defined because G is in C1. But you have, in some sense, proved this using regularity structures, and in fact, you could have done this with rough paths and so in lemma, etc. So I had tried to explain, so to mention this problem of, so until you are at this level, there is no problem because these are symbols and these are functions. When you apply pi t, it is still good because in S you have distributions, but in T you have functions, and the two variables are decoupled. But when you reconstruct, the operation is much more complicated. So it's a deep theorem that you can couple the two variables. Okay, and this extends the standard, the classical operation when everything is continuous. Okay, does this explain better? So, so by the way, yesterday I had written this, which is the same but in the general case, so I repeat it. So you have families, okay, sums of symbols multiplied by functions. This is u of x. The distributions are inside pi, so again, this is a distribution, and there is no problem as long as x and y are decoupled. When all the distributions are in fact continuous functions, then you are in the classical setting, and the reconstruction is this operation. So I had written this, and now, okay, for, say, it is an additional information which may be instructive. So in fact, this contributes only as long as the homogeneity is less or equal than 0, because otherwise this, when it is positive, this is supposed to be bounded by y minus x to the gamma, so to the, okay, homogeneity, which vanishes. So this plays a role in the formula. When you compute, in fact, all terms in your expansion which had positive homogeneity disappear. Okay, I can make the example here. Okay, if I compute pi t u t of t, I get x of t, which is the value of my object. Okay, so it's absolutely correct. While the other objects give me other informations, they give me like for instance, this would be the derivative. Okay. Okay. Good. Let's try. Now, okay. Yesterday we discussed these operations. Okay. Yesterday we constructed this lambda map, solution map, from the space of models to distributions. Maybe maybe I can repeat this in a second. Okay, what we have also done was to start from a regularized noise and construct a canonical model. Okay. What remains to show is that you can change the model, which is what is called here the renormalization group, and then prove that the model converges. Okay, yeah, you remember that the construction of the canonical model was done before. Sorry, I go back. It was this. These slides where I had all these functions which are explicit. They depend only on xi and on k or g. So, and the same for the pi. Okay. I told you that this is not meant to probably to converge, and that you have to modify it. Now I have done these computations yesterday. So what I essentially have tried to explain is that for any model, I repeat, for any model, you can define this space of model distributions, and then you can set this fixed point. Okay, so then you have to prove that this is a contraction if the time is small enough. Okay, we trust Martin for this, but the form of the equation is the same for any model. So I tried to insist on this. And then something changes, and also this expression is the same. Well, sorry, no, this is not complete. The final expression is this one, so there is some function phi, some function nabla phi, which will depend on the model, but the form of the equation is the same for all models. And then what changes is that when you reconstruct, so when you go to the distribution below, this I did here for the canonical model. So here you start canonical model. So you reconstruct, this is this. Here you use the commutation between integration and convolution. And once you are here, you have reconstruction of a cube. Okay, for the canonical model, it turns out that since the canonical model is multiplicative by definition, then the reconstruction of the cube is the cube of the reconstruction. So the two operations commute. But then I said that this is not true in general, and this is not going to be true when we renormalize. So here you find the PDE you started from, but then you want to renormalize this and verify whether there is another associated PDE. Okay, now this is not simple, but let try. So I have to describe a group action on the space M of models. So there can be many group actions, okay? So here a bit the game is to have one which is as simple as possible, as small as possible, okay? You want a finite dimensional group, maybe okay, if possible a two-dimensional group, because we said that in quantum field theory they already know that there are two relevant constants, so one which is like 1 over epsilon, one which is like log epsilon. So we would like to find the same here. Okay, let's see. So this is very incomplete, okay, but I try to give you the main idea. So we want to represent this action by some linear maps on my trees. Okay, again, my trees form a space with dimension 13 or something like that. So I want to express my renormalization maps in this way. Okay, sorry, by the way. Another mystery for me is why we use the same expression renormalization group. Okay, so this may be another project for the semester, okay, to clarify why we steal each other the words. Well, this is your point of view, so I may say the same. No, I won't. Okay, let's see. So for every M in this group, okay, class, so there will be a way to go from pi gamma to pi m gamma m. Okay, so the property that I want to have is the following. So if my model is made of continuous functions, which is the case for the canonical model, then I want that pi m x of tau at x is equal to pi x of m tau at x. Okay, so you will see why this plays a role. Well, of course, it plays a role because it's related to the reconstruction. So the reconstruction based on m goes through this, but then this is exactly what I do. Then I can replace pi x m by pi x m like this. And okay, I'm going to show you again some computations. But notice that in general, it is not true that that formula holds for any y. It holds only at the point x. So again, because for y different from x, there are terms here which can go to 0. Okay, because there are terms which are positive homogeneity. So this formula does not see terms in this sum which have positive homogeneity. Okay, but this formula sees them. So there is okay. Anyway, so this is clearly weaker than this. Yes. In your transformation, do you want to rescale epsilon to? Yeah. So this is the general. Okay. Then the constant will depend on epsilon. So this is going to come in a second. So okay, sorry, let's see. No, okay, I will say this in a second. So we are going to consider m of this form. So there are two constants which will depend on epsilon. Okay, so it will be m epsilon. Okay.
But do you rescale epsilon?
Okay, my terminology is that epsilon goes to 0, okay?
Okay, yeah.
Yes.
So you're decreasing epsilon.
Yes, of course. So I have regularized, so okay, maybe I can repeat this. So epsilon is inside the regularized noise. Okay, so epsilon will go to 0, but by removing the regularization you get problems, and you try to cure these problems by putting this action which depends on epsilon as well. Okay, I try to do this quite explicitly. Now, this also may be familiar to many of you. So in fact, what you want to do is to contract diagrams which can diverge. Okay, so this will also become so these are two trees of negative homogeneity. So this one has homogeneity -1 minus something, and this corresponds to 1 over epsilon, and this has homogeneity minus something, and this corresponds to log epsilon. Okay, so but for the moment I am just constructing an operation on trees. So this means that every time that I see this cherry, I extract it. Okay, and for instance here, of course, I have 3 possible choices, so I get these 3. Here I am extracting this cherry at the root, so I get this. Here I am extracting L2, and so I have to choose which one of the branches on the top I leave, and therefore it's again 3 times this. And here I have nothing to extract, so it's 0. Okay, so you see the idea. Yes.
If you apply L1 on the tree that is used in the definition of L2,
This one.
can you remove the top cherry?
Okay, good. Yes, but it's similar to this. When you remove the top cherry, then you get something like integration of 1, which is 0 by convention. Okay, so this happens also here. L1, you remove this cherry and you remain with this edge alone, but this will be put to 0. And by the way, so here you have an exponential, but of course these maps are nilpotent, so it just means that if you need to apply it again, you do it, okay? But, okay. So I have done this exercise to write explicitly all terms. So m of psi psi, m of this is this, m of cherry is cherry minus its constant times 1. So m of this chicken fingers, you know, is themselves minus 3 c1. Yes, it's correct. This, yeah, this is simple. It's the same. Now again, this would be this, but by convention you put this to 0. Here it's the same. So you, in principle, you would have the cherry extracted, but you neglect this. Okay, here you can contract the whole tree, and you get C2 times 1, and then you can contract the cherry below, and you get this. Okay, and the third line, so the fourth line is a bit more complicated because you would have other trees here. So for instance, here if you contract a cherry above, so you find a tree which is the following. So we have one edge, then another edge, and then this. Okay, this was not in my initial list, if you remember, and in fact it has relatively large homogeneity. It is 1 minus something. It does not play a role in the following. So in fact, in principle, I should include also this tree in my space, and I have an action on a slightly larger space. But in fact, this does not play a role, so I neglect it. The same for this. You get a tree like that, which does not do much. And the same here, so this plays a role. Of course, you extract the second tree and get this. Plus, you can extract only a cherry on the top, okay. You can also extract the cherry. Yes, yes. But again, that's positive. So in fact, it will not appear in the computation. So yes, no, it's true. You can also extract the cherry. Yes, please.
I didn't understand the middle one and the middle line, the third line down. That one, because isn't there one left over? If you contract two of them, you've still got a cherry with a line on it.
Yes. Well, you get this, correct?
Yes.
Okay. Again, this has
Stuff. You should have written plus stuff.
plus.
This is on the same level.
I can also, yes, maybe I should have. No, yeah, they're right. That's 0 because it's yes, that's right, because it's like I of 1, and so this is 0. Yeah.
Oh,
Okay, but
so I see. You are killing all the loops.
yeah.
Okay.
Yes. Yeah, thank you. Okay, and then what's the point of this? So then you remember this complicated expression we computed for psi minus u cube. It was all this bunch of terms, and then what you do is you apply m to this. Okay, I've done this line by line, so this becomes this becomes this, blah blah blah. So in fact, if you remember, this was meant to belong to a space d kappa, with kappa small. That's why I have neglected all these trees, because I am interested only in trees of homogeneity less than kappa, which is very small. So essentially from 0 down. Okay, so anything which is relatively smooth is irrelevant. And so, okay, maybe it is not so interesting to follow all computations, but so the point is that you find mu cube here plus this remainder, which comes from, let's see, so 3c1 times this, then you have 3c2 and there's a 3 times this, and see it's here. And okay, the magic here is that the same constants multiply also phi 1. Where are they? So this is 9 phi c21, and then this one 3 phi c21. Okay, and this is equal to m of u up to, again, positive terms. So modulo positive terms, I obtain this this formula. So yeah, so this is the magic. Of course, if the constants are 0, then I am back to the identity, and okay, it's consistent. But now if I apply the reconstruction, I define u hat as Ru, and okay, this is the reconstruction of this, and this is the reconstruction of this. Now, there is clearly some form of magic. So what is the magic? So, a priori, there was no reason why, in the end, I would find something which was closed in mu. You see? So this is the magic. So at first, I find this term. Okay, if I had, if ever the two constants had been, no, sorry, so the two terms multiplying the two trees had been different, I would have lost. Okay, so it turns out that this perfectly And in fact, this is a general fact, so this is the point. It's not particular of 543. It's okay. I will come to this later. Okay.
But why you say it's like didn't you define M in some way such that this works, or
No.
doesn't
So
follow how you define M? But
well, this is how I define M. So. So maybe my understanding of all this is still only partial, so certainly, but so I think that so again, then now there are theorems which guarantee that, but at this level it's quite so I don't know. So I don't see why from the beginning you define something like that, and you are sure that at the end this will be a closed expression in MU. So
why did you choose precisely M1 and M2? You didn't explain why you defined M that way, or didn't.
well, I said that okay, I said that these were two trees of negative homogeneity. So these were objects which were meant to explode in some way.
They're the only ones.
No, okay, they are not the only ones. Okay, let's go back to the list. This is the list. So, okay, this is negative, this is negative, this is negative, this is negative. So all these are negative until here. Okay, so it turns out that you extract only this one and only this one, and this is enough. Okay, this is a good question. Where are the other experts in the room? So why are these two enough because many turns out to be zero, right?
So which two are you talking about?
I mean, why do we extract just two trees? Okay, and not this one, and not this one, and not this one.
Well, those have expectation 0.
Yeah, okay, yeah, or rather, so the BPHZ thing, yeah.
I mean, if you kind of use a different sort of modification of the noise or drive it by a different noise, then those will produce commentary.
Okay,
For
yes.
instance, you can see
Yes, of course. Yeah, sorry, okay, that's right. In fact, because, okay, this is a relatively simple situation, but otherwise, of course, you have to you have to extract 5 trees, which are probably 1, 2, 3, 4, 5 exactly. Yeah. Yes. So I am simplifying here because this is just the Gaussian modification, etc. But in general, you have to extract all of them.
Oh, I see.
Yeah.
You don't want any 5 cubes and, yeah.
Now, for instance, you can start from a psi which is not Gaussian. Then you will have a more complicated cumulant structure, etc. But of course, at the first presentation, this is not what you want to do. But in general, you have to extract these 5 trees. In principle, even if psi is not centered, you also have this one. So
also, you somehow define this m by this exponential.
yeah.
So somehow in the exponential, it's encoded something that you will get somehow your miracle of having the same terms maybe comes from that.
Maybe. So do the other experts, Ivan?
I mean, at the level of the perturbative expansion, it's sort of clear that if you perform this sort of contraction thing, that you can kind of do this by rewriting the equation. The hard part is to check that the non-perturbative parts play along. So at least at the fully perturbative level, you can see if you perform this contraction procedure and the expansion of trees, then this comes from a renormalized equation. It's
Yeah,
just
but the goal is to get rid of perturbatives.
That's right.
Okay.
Is it correct to say that M is defined in such a way that the final equation is revealed?
That's right. The space of all m's has this property. Any way that you deform these products. Yeah.
Yes. So anyway, M, yes, yeah, I didn't mention this, but so you want to conserve the space of models, okay, which is nonlinear. So of course, this put a lot of constraints on your maps. And okay, it turns out that this property of preserving the models then guarantees that you preserve also the form. So this fact. Okay, so now you see in the now you see what? You see that here I forgot the u. So u equal to this is the same form of the equation in all models, but then when you reconstruct, what I mean by this is that I start from the canonical model, and I use this M map. Okay, so I have u hat cube plus this additional linear term where I see the two constants appearing.
These are two arbitrary functions of epsilon.
What are arbitrary functions?
C1 and C2.
Yes, for the moment epsilon is not even there, so it's any couple of constants, yes. Because now epsilon is still fixed. When I want epsilon to be to go to 0, this will have to be chosen accordingly. Okay, what comes next? Yes, so this comes next. So if the canonical model fails to converge as epsilon goes to 0, then we try to renormalize it as above using a map M epsilon, which depends on epsilon. So we define those M, so P hat, so pi hat epsilon, gamma hat epsilon, associated to a linear map M epsilon in such a way that, again, we have this property. Okay, so from now on, when you see the hat, it's renormalized in this way. So I have not yet fixed the constants, but I will. Okay. In fact, the maps M epsilon do not converge either as epsilon goes to 0. Okay. On the contrary, they contain these divergent constants. So in a sense, I am so there is a story here of change of parametrization. So I am reparametrizing my space of models in such a way that object pi epsilon, which was diverging, so in fact I see it in a different scale, and I see it converging. But again, there is certainly some connection with what people in QFT know well, and it would be nice to make it clear. Yeah, all this should be very precise to what happened in QFT, but I don't know how. Okay. Now, let's see why. So, how you choose these constants? So we must choose Ci equal to Ci epsilon for I equal 1, 2. We introduce, in fact, a simpler object here. So we replace pi by this, so boldface pi epsilon, which looks like the model, but it's simpler. So the main difference is here. You don't do this. There is no base point anymore. It follows easily the definition. Okay, so the convolution with k when you want to integrate, and also here there is no. Okay, 0 is the base point if you want. That's arbitrary. Okay, in fact, we will discuss the convergence of these objects, and it turns out that this is good enough then to prove. It's very complicated, but it implies then the convergence of the full model. So let's see what is this pi epsilon of Cherry at z. So this is just k convolution xi epsilon at z squared, which is equal to this. Okay, so by this I mean this is the integral with respect to the white noise, if you want, and then I have put the convolution on the kernel. Okay, and then the renormalized model is defined this time really just like this. It's pi hat epsilon, so the boldface pi is boldface pi epsilon m epsilon. So this is really precise. This was not true at the level of the pi x, but it is true at the level of this pi, so it's much simpler. Where again, so m epsilon is this thing. Okay, so let's see what happens for the cherry. So the cherry was the square of this, okay, and now so you do a standard decomposition in the Wiener chaos. So you have so this is the inhomogeneous Wiener chaos of order 2, and you have one term of order, so homogeneous of order 2, and one term homogeneous of order 0, where the order 0 is just the expectation. Okay, now the expectation is, okay, everything is written in this diagrammatic notation, which may sound familiar to some of you. So the green dot means the variable z. Okay, these edges are k, the kernel k epsilon computed at the difference of z minus z1 and z minus z2. And then these round dots are so appearances of the noise. While, okay, this you see is this expression, so z1 is common to the two kernels, and then you write it as a loop. So finally you see loops in the theory as well. They are not just trees. Now, since this by translation invariance, this is a constant. Okay, so you write the green dot, but in fact it does not depend on z.
So the integral over z is space-time now, right?
Yes, yes,
And if you
yes.
do these integrals, so in Anti's lectures, these integrals were only over time, but I guess because it's the heat kernel, you get the same numerical factors, despite that this is a space-time integral. Is that right?
There was
When
no.
you do the time integrals and
Well,
the
the
space-time
space-time
integrals, they
integral,
become.
the
Yeah,
space-time
but
heat kernel
the
get-
counter term doesn't depend on the. I will explain it, that's fine.
Okay.
So there was no time in Ante's lecture, no?
Yeah, but
No,
the
it's not
numerical
space.
factors are still the same, right? The numerical factors are the same, not
The numerical factor. Okay.
Yeah,
Yes.
the same, yes.
Okay. Yes, please.
No, that's right.
No.
We were just setting something. Yeah,
Okay, so well, I have one constant. I choose C1 of epsilon as this integral. And so then, if you check the definition, so pi hat epsilon is just so the first of the two terms, this one. So you are recentering this variable by subtracting the mean. So in this case, the renormalization is a recentering. Okay. Now it turns out that okay, of course, this object was diverging as epsilon goes to 0 because this because the homogeneous term of order 0 was diverging, so there was no chance that this can converge. But if you remove that, well, it turns out that what remains converges now with respect to z again. This will be a random distribution on RD, and okay, you can prove with some estimate that this converges in probability as a distribution when epsilon goes to 0. So again, renormalization reduces to a centering operation, like so going from x squared to x squared minus 1 in Hermite polynomials. Okay, it's the same. At this level, it's the same. Okay, now let's see the most complicated tree of the whole bunch. So Okay, this is pictorially very nice, but so again, this is a decomposition in the different homogeneous cases. Okay, so here we are at level 5, so this is level 3, and this is level 1. Okay. Okay, now, okay, it takes a few computations, but now you want to apply m epsilon to the tree, okay, and then compute pi epsilon of this. So this is your renormalized model. So the result is this. Okay, I'm sorry, this should be C2 epsilon. Okay, the action of C1 at this level is to cancel a few of the terms of the previous slide. So again, this is a sort of like a mid polynomial, so weak product type. Okay, and then you remain. Okay, the first two turn out to converge, while these are still diverging. And then, so this is a very important fact. You cannot choose C2, sorry, or C3 in such a way that these two terms cancel. This is impossible because the structure is different. So this is essentially, you see, if you choose, this is the best possible choice, C3 in this way, okay, then you multiply a constant times this tree. While here the same tree is not does not depend on z, it depends on one of the variables which are being integrated here. So these are two different objects. So the best you can do is to hope that these two objects compensate each other. But this is much less trivial than outright cancellation. Okay, so you must show that these two distributions okay, define by subtraction one distribution which is well defined in the limit. Okay, maybe I could have written this on a slide. So maybe I have 1 minute even just to show you so what's going on. So in the kind of object that you find in the limit is the following thing. So this difference, okay, let's call it T epsilon. It's a random distribution. You apply it to phi, which is C infinity 0 over 4. Okay, this will be some kernel which should have a name. Okay, kernel, okay, of x. Now this will be non-integrable, okay, at 0, say. So you cannot just multiply by phi of x and integrate in dx. So the action of this subtraction is to do the following. Okay, and cure the non-integrability at 0 of this kernel. Okay. So again, this is something known in the physics literature, but okay, in a sense, this is extremely well so suited to the whole business of regularity structures, because again, this is a Taylor expansion, but now it's on the level of the test functions. Okay, and again, there is the theory says that in principle, if here the kernel is of a worse order, here you may go to the next order, etc. Okay, so there is a whole treatment of this, but for 543 you stop at this level. But you see that renormalization is not only about weak products. Okay, it's more sophisticated than that here. Okay, and the other trees are treated in the same way. So it turns out that again, in this simple situation, these two constants are enough to obtain all negative trees which converge. Okay. Okay, so I have two more final slides, then I stop. So again, so I summarize the procedure into 4 steps. So one step is construction of the space of models and continuity of the solution map. So this we discussed. An algebraic step is the renormalization, this group action on models. A third step is convergence in probability of the renormalized model, which we discussed last. And say combinatorial or second algebraic step is so computation of the equation solved by U hat, which is this place where you see the counter terms. So the new PDE, the renormalized PDE, which appears. So you obtain a renormalized solution, U hat equal to lambda x hat, which is also the solution of a fixed point problem, at least okay, at the level of the D gamma space. I said something about that. So in fact, this works for general noises, far beyond the Gaussian case. Although someone asked me, why do you care about the non-Gaussian noise? Okay, so this maybe is not interesting for QFT, I don't know, but it's very interesting for probability and even analysis. Okay, and then so let me say, so the first paper by Martin so introduced the theory. In particular, gave a very general construction, so of the a very general solution to the first problem. Okay, then it applied this to 543 and to 2 more situations, but the rest of the argument was ad hoc on the models. Okay, so this did not make regularity structures a theory yet. Okay, so there has been a lot of work since the paper appeared on Archive in 2013, so it was 5 years ago. Now these 4 papers together are a theory in the sense that they give general theorems on how to do all what I've shown you. Okay, all this, so how to choose the trees, how to perturb, so how to renormalize, how to prove that the thing converges, blah, blah, blah. So there are theorems which say that. So you have a automatic black box. So it's really okay. Sorry, I'm one of the co-authors, so I'm not objective, but it's really very, very fascinating. It's very difficult, but at the same time, so a physicist in Paris told me that in QFT, so if you want to make all details rigorous, so it's a book for every model. Okay, so here there is one book, but which covers really a large class of applications. Okay, so then there is a story of short time, long time, blah blah blah. I'm not saying that okay, the history is finished, but there's really been an effort to understand this technique very deeply. So by the way, you can notice that the first has been published, but the other ones still struggle, like Felix said, so the world is not ready yet to it's too bad for the world. And this was my last slide. Thank you very much.
Why does not work 4544?
Ah, okay.
Which is the reason?
Yes, good. In 544, so there are several reasons. So, in some sense, none of the steps work. So, what is it? So, for instance, you will have infinitely many trees of negative. So so like this list. What is it? Sorry. So this list becomes okay of negative trees becomes infinite. So you have to control infinitely many trees. The lambda map. Sorry, I'm doing a mess. So the lambda map is not known to be continuous in this setting. So maybe there is also some problem of convergence. So again, I'm not so expert of all these details. So AJ. So for 544, so even if one could construct a renormalized model, so would there be any chance of proving some convergence?
I mean, yeah, I don't think you'd have any sort of continuous solution map.
Yeah, no, that's I said, yes, but
the actual model, I mean, the problem is that the topology on models depends on basically a certain finite number of negatives.
Yeah, exactly.
So
but then you have infinitely many. So
you have a new topology on models.
Exactly.
Convergence wouldn't give you any.
Yeah, exactly. So again, here you have infinitely many terms to control, and the continuity of this map breaks down. So
you might not be proving what you should be proving also in 4 dimensions, because as Antti said, the theory that exists in 4 dimensions is, roughly speaking, the coupling constant with the wrong sign, which, I don't know whether the sign of the coupling constant plays a big role in it. It doesn't actually play a big role in what you do, but you want the other sign. If you want to, I mean, the invariant measure that goes with it is associated with a wrong sign coupling constant.
For short times, it doesn't matter.
Yeah.
Yeah, that's a yes. When you do this analytic business, you don't mind.
So maybe
that's for a long time.
That's actually a nice thing about this is that there's a problem, sort of not all the way to getting an invariant measure. I mean, invariant measure is going to be a difficult problem for that, and, but this is good because you can have a short time existence.
Well, I propose to continue the discussion of the coffee break. So thanks.
Thank you very much.